Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the structure determination of citral because we are discussing the monoterpenoids, and in the monoterpenoid we have considered as a citral. In that citral, what in which class it is belonging, where it is occur, how it can be isolated, what are its properties, what are the uses of citral, and then later on we have discussed structure determination of the citral. First of all, we have considered the molecular formula, that is the first step required for the determination of that citral or the terpenoid. So molecular formula we got for citral is a C10H16O, and after that we have discussed second point, that is a detection of unsaturation. And detection of unsaturation, as we know that there are the regular method for determination or for detection of saturation. One is a bromination, another one is a hydrogenation. Both the reaction clearly indicate that there is a presence of two carbon-carbon double bond in the citral. By observing or by analyzing its product, we can confirm this one, or we can prove there is a presence of, because the question, what type of the question appear in the exam? In the exam, the questions appear like this: how will you prove the presence of two carbon-carbon double bond in the citral? There you have to remember the general formula of that citral. On both the side you show the arrow. On one arrow you have to write down as a 2 moles of bromine, you will get as a tetrabromo derivatives, and in the other hand you write on the arrow 2 moles of H2 in presence of the catalyst such as nickel, platinum or palladium, known for the hydrogenation, and then you are getting as a tetrahydro derivative. Both these reactions confirm that there are two carbon-carbon double bond present in the citral. That's it. Then next one we have seen, that is how will you prove the presence of acyclic or the open chain structure of terpenoid. And as we know that formula for parent saturated hydrocarbon of citral becomes as a C10H22, which correspond to a general formula CnH2n plus 2, suggesting that citral is a open chain terpenoid. That's it. Then after that we have learned as a fourth point, that is the nature of oxygen. As we know that nature of the oxygen atom, when the molecular formula containing an oxygen atom, then or the citral has a molecular formula C10H16O, there is an oxygen atom, and that oxygen atom may belong to the different functional groups. And as we know that while studying the general method for structure determination of terpenoid, and therefore we can easily find out what type of the nature of that oxygen atom in the citral. First one we have considered, citral forms an oxime with hydroxylamine and bisulfite addition reaction with saturated sodium hydrogen sulfide, and therefore citral contains either aldehyde or the ketonic group. We confirm there may be a carbonyl group. That carbonyl group may be aldehyde or the ketone, that we come to know right now. Then another one, Citral on reaction with sodium amalgam in a dilute acid form a primary alcohol geranyl, and Citral on mild oxidation with moist Ag2O gives xeranic acid which without loss of carbon atom, and both these reactions confirm the presence of aldehyde group in a citral. So that is there, the aldehyde group present in the citral. How will you prove the presence of aldehyde group in a citral? By doing these two reactions, by performing these two tests, we can confirm there is a carbonyl, there is a aldehyde group is present in the citral, no doubt about it. Now, where the aldehyde group is present, where it is present, so that there we are going to perform the test, the position of aldehyde group. Aldehyde group we know that now, but where it is present, that we are trying to find out. So for that purpose also we are performing some of the tests. Test number A, the UV spectrum of citral shows an intense peak at lambda max 32 nanometer, which is a characteristic of conjugated aldehyde. Do you know ultraviolet? It is one of the spectroscopy which provide the information regarding as a carbon-carbon double bond, whether it is in a conjugated or in a isolated form. So that type of the information that ultraviolet spectroscopy provides us, and therefore while analyzing the spectrum of that UV spectrum of that citral, what the chemist found that there is one intense peak at lambda max at 238 nanometer, clearly indicate that there is a unsaturated, which is a characteristic of conjugated aldehyde. So that's it. And now another one, citral on hydrolysis with aqueous potassium carbonate solution under high pressure gives aldehyde and a ketone, that is methylheptanone 6-methylheptene-5-en-2-one, that is a IUPAC name of that compound that we got. Both these reactions prove that citral contain both reaction proves that citral is a conjugated aldehyde, alpha beta unsaturated aldehyde. So up till now we have discussed in detail. Today, right now, we are going to discuss the next point, that is a carbon skeleton in citral. That the point we are going to learn over here. Carbon skeleton in a citral. What type of the carbon framework present in the citral, that we are going to learn here. And now for that purpose, citral when heated with the citral when heated or boiled or reflex heated with KH-SO4, that is a potassium hydrogen sulfate, undergoes cyclization to form undergoes cyclization to form paracymene, to form as a paracymene. So that the product we got over here. Citral when treated with KH-SO4, which is a potassium hydrogen sulfate, undergoes a cyclization to form to form para-thymine. So as we know that citral has the molecular formula C10H16O, which is a molecular formula of citral. When this molecular formula is further treated with this reagent KH, saturated KH-SO4, that is heated or boiled, what they got? They produce, or it produce the compound like this. Here the methyl group, here the isopropyl group, and this compound is nothing but the para-thymine. Para-thymine, which is a common name of this compound, which is aromatic, and the methyl group and the Zem-diomethyl group or isopropyl group, which is present at 1,4 position. So that suggests that the carbon framework of this framework present in the citral, and formation of para-thymine proves that citral contain a carbon CCH3 and isopropylene and CCH3. We know that this CCH3 and isopropylidine means Zem-diol. Isopropylidine means Zem-dimethyl. Isopropylene is nothing but as a Zem-dimethyl. As we know that both the methyl group, they are present on the same carbon atom, and that's why it is known as the Zem-diol, vicinal Zem. That type of the thing we are going to learn while studying as a spectroscopy. Here just remember there are these 3 carbon atom in the 1,3 position, so that type of the position is called as a Zem-dimethyl. Is isopropylidine group is nothing but as a Zem-dimethyl. So suppose as a question may come in exam, what kind of the nature of that question? They are going to ask, how will you prove the presence of Zem-dimethyl in the citral? So what will be your answer at that time? There you have to just mention that citral, then do the arrow, on arrow write down that reagent KHSO4, heat it or heated, boiled or reflux. The resulting compound form is a para-thymine. That clearly indicate that proves that the citral containing as a isopropylidine group or the Zem-dimethyl group in a citral. That is, in that way, in a systematic way you have to answer it. You will get as a full mark, means 1 mark question. If it is appear in the exam, you have to mention, you have to write down the answer of that question in what I just mentioned over here. So that's the way of doing answering that type of the question. By considering all above reaction, the possible carbon skeleton in citral are as follows. By applying all these, now we got the carbon skeleton. So we can draw the carbon skeleton now, whether it follows the Isoprene rule or special Isoprene rule. Now we know that there is a carbon atom, then here also is a carbon atom, then carbon atom, then here also has a carbon atom, and one more carbon atom we can write here, or we can write another structure here, carbon framework or carbon skeleton we can write here like this, here, then carbon atom. Another way of showing that carbon skeleton like this. So here we got number of carbon atom are, how many are there? C 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is the first structure you can call it, and this you can call it as a second structure. Here also 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. 10 carbon atom, because we are trying to find out the carbon skeleton. And now let us apply that rule, isoprene rule and the special isoprene rule. Isoprene rule means what? The carbon whether they are joined to head to tail, that is a special. If you remember here, this is a branch side, so you can designate as a head over here. Now 1, 2, 3 and 4, here you can call it as, it may be as a tail over here, right? Tail. And then here again this may be as a tail once more here. Then here it may be as a head and tail. It is not joined. Suppose if you remember from here, this is a branch side, so it is head, it is a tail, but there while joining this tail and here must be as a head, but this is not the not obeying the special isoprene rule. If you see over here what is that? Here if you remember, carbon is branch side, so it will be the head, and you go this side, this will be the tail. Now if you remember here carbon again it is a branch, so it will be the head here and it will be the tail. Now the special isoprene rule says that those terpenoid or those natural product are follows the special rule or isoprene rule that are the natural product. This is a wrong, you can call it as a wrong, and this will be the isopropylidene group, that is a right. Second one is a right, RIGHT. Right means this is a right because it obeys the special isoprene rule in this way. By considering all above reaction, the possible carbon skeleton in citral are as follows, because this is a methyl group. This is a methyl group over here, and this is the what we can call it as a, this is a isopropylidene group. This is a isopropylidene group over here, and both are present in the citral. From that we come to know that there is a, the skeleton first is ruled out. The skeleton first is ruled out because it does not have head to tail linkage of isoprene units or special isoprene rule. The skeleton second follows special isoprene rule and is further confirmed by oxidative degradation reaction. So let's see, seventh one is the oxidative degradation reaction. 6 point we have just now discussed over here. We have found out the framework or the carbon skeleton, what type of the carbon skeleton present in the, or how will you prove the presence of carbon skeleton in the citral. So how would you answer? By doing this one, oxidative degradation. 7th point is a oxidative degradation. Oxidative degradation. Oxidative degradation, it is one of the method. If you study the degradative product, we can find out the position of double bond present in the unknown compound, specifically in this case is the citral. Now let us see first one over here. So this one, citral on oxidation with alkaline potassium permanganate followed by CrO3 gives acetone, levulinic acid and oxalic acid. When the here citral on oxidation with alkaline potassium permanganate KMnO4. Look at here, citral on oxidation with alkaline potassium permanganate followed by CrO3, that is a chromium trioxide gives acetone, levulinic acid and oxalic acid. That are the product obtained when you carry out the reaction with alkaline potassium permanganate followed by chromium trioxide. Now let's see here, as we know that the general formula of citral is a C10 H16O. First reagent we are adding, alkaline KMnO4 potassium permanganate followed by CrO3. After adding this reagent, the product formed over here, what type of the product we are getting? The product are acetone, as we know that acetone C double bond O, then here maybe as a CH3. Another product is a levulinic acid. As we know that the structure of levulinic acid will be this one, C double bond O, then COOH. This is the structure of levulinic acid, and the another structure is the oxalic acid, COOH, then COOH. That is the oxalic acid. These are the structure we are getting by doing these things. So now is the second point, when citral, or what we can call it as a ozonolysis. As we know that ozonolysis, it is a process of breaking down carbon-carbon double bond, and we are getting as a formation of the product. Ozonolysis of citral gives acetone. Ozonolysis of citral gives acetone, levulnaldehyde, and plus levulnaldehyde and glyoxal. What is that? Glyoxal. These are the product obtained when you carry out the reaction of ozonolysis, or you perform the process of ozonolysis. Starting compound is this one, as it is a citral having as a molecular formula C10 H16O. When you treat with O3 ozonolysis, that produce acetone once again plus levulnaldehyde C double bond O. This one, instead of COH, here will be the CHO aldehyde group, and here acid group here must be as a aldehyde group, and therefore this is nothing but as a acetone once again. This will be the levulnaldehyde, and this will be the glyoxal. These are the product we are getting after doing all these things. So formation of acetone in both reactions shows the presence of dimethyl group in citral. From all above reaction, following structure is assigned to citral. Whatever reaction we have obtained by adding different reagent, we are now at the final stage. By considering all above reaction together, now we are able to assign the structure of the citral. And let's see, by following all this reaction, finally we are getting the structure of the citral. Now here onward we are come to know that what will be the structure of the citral. By look at the structure of citral will be this one. Here CHO double bond, one here, another one double bond, this methyl group. So this is the structure which we got here. This is the structure of citral. If you find here molecular formula, how many carbon atoms are there? Carbon atom are C10. Count over here, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. H16. Is there X6 here? 3, 3 or 6, 7, 8, 9, 10, 11 and here are 3, 11, 14, 1, 15 and 1 is a 16. And how many oxygen atoms are there? Only one oxygen atom. So it fulfilling all this, and this is the open chain. That is the correct structure of the citral we have got over here. And with this structure, the above reaction are summarized as follows. Reaction of citral. The final structure of the citral is confirmed by its synthesis. One of the synthesis of citral by using as a Barbier and Boult synthesis, that we will see later on. But let us see, this is a structure of citral. Now with this structure, the above reactions are summarized as follows. Let us see here. Suppose this will be treated with sodium amalgam NaHg in presence of dilute HCl, right? That is a reducing reagent. What it gives? It gives the Giron oil over here. What is going to happen? This will convert aldehyde group into as alcohol, so that you are going to get here, and the double bond remains intact here. Here we are going to get CH2OH. This is nothing but as a Giron, right? This is one of the reaction we have seen. And when if it is oxidation carried out in presence of moist Ag2O, that is a silver oxide, what is going to happen? This is a mild oxidizing reagent. What it will do? It will convert aldehyde group into as a carboxylic group, and therefore you are going to get here COOH. This double bond remains as it is. Other part of the reaction remains as it is. This is nothing but a geranoic acid. This is a geranoic acid. This is a product which we are getting over here. And suppose if you do the ozonolysis over here, ozonolysis O3, what you are going to ozonolysis? It is a process which will break the carbon-carbon double bond, and we are getting as a fragmentation. If you break from here, what you are going to get? Here you are going to get double bond oxygen atom over here, and here CHO, or here again as a CHO, this one, and on that side this one, this double bond is going to break over. Here you are going to CHO, and here is a acetone. This is a product. This is a acetone, glyoxal and the lavanaldehyde, that is a product which we are getting over there. If it is treated with alkaline potassium permanganate followed by what we can call it as a followed by this one, first one KMNO4 and second will be the CrO3. This is also what they are going to break. This is also as a degradation product. They will break the carbon-carbon double bond, and what you are going to get once again C double bond O over here, and then here also as a, but that COOH, and this is become as a COOH oxalic acid, COOH oxalic acid, and one more product, that is a acetone when it is breaking from here. So this is again as a levulinic acid, this is oxalic acid, and this one will be the acetone that we are getting. And when it is treated with, suppose heat it in presence of KHSO4, it produce this type of the product, methyl group, and this is a parathymine. This is a compound obtained, that clearly we know that. And when this compound further treated with, what is that, boiled with K2CO3 potassium carbonate, if you boil it, what it produce, it gives the heptanoic acid here like this, C double bond O, then double bond, this remains as it is, and one more product obtained over is a acetaldehyde, CS3 C double bond O and H, that is acetaldehyde. These all the reaction will be getting over here. If you these reaction, all these are the reactions of citral. How we are getting all these reactions of that citral that just now we have seen over here. Look at once again, this is the structure we have derived, we have obtained by doing various tests, by performing various tests over there, and finally we are derived the citral structure of the citral, which has molecular formula C10H69O, and when whatever reactions are carried out, all we are using over there, according to that all the product we are getting, and that confirm that that is the correct structure of the citral, which follows the isoprene rule as well as special isoprene rule, because here we have seen the carbon skeleton, what type of the carbon framework present in that terpenoid, that also we have seen. So tomorrow we will learn the synthesis of citral, what will be the starting material of that citral, how we can achieve it, is there any named reaction involved while the synthesis of that citral, that is the final point remaining over here. The final structure of the citral is confirmed by its synthesis, because we are going to synthesize that compound in the laboratory starting from the known compounds, and we are going to derive the structure of the citral. So I think remaining that synthesis of citral, actual synthesis of citral, we will see in the next lecture. With this, let us stop today here. Have a nice day. Thank you.